So good morning. I hope I can keep you entertained given that I am standing between you and lunch. You've just heard my colleagues talk to you about how we can rewire humans by altering their genetic code. And I'm going to tell you this morning about a different code. And that code is the neural code. But in decoding what our nervous system says, something else really fundamental comes up. And I want you to hold this as I speak to you today. And that is, how will connecting humans to machines make us something other than human? Something to think about. Now, we're going to start this by talking about mind mapping, brain mapping, and how we can actually read minds. Again, the neural code, and we've actually learned a lot about it. Here you see some beautiful neurons. These are actual nerve cells that have been stained, and we're looking at them under a microscope. And we can actually listen to them. And neurons speak with rate codes, timing codes, pattern codes. And in the process of deciphering this, we've actually gotten to the point where we can learn things. And in fact, what you see here is the best way to listen to neurons. It's actually by putting electrodes directly onto the surface of the brain. Yes, this is actually a real brain. Now, the nicer way to do this, so we don't have to crack open your skull, is actually to put the electrodes on the outside. So this is an electroencephalogram. And here what you see is that the leads are on the skin. Now, these are really, really accurate in time, but not so accurate in space. And the reason why is that there's skin, muscle, bone, fat in between the electrode that's measuring the electrical activity and the surface of the brain. And so what did we do? We found ways to actually look deeper inside the brain. One of these ways is magnetic resonance imaging. It's the ability to actually use magnets to look at blood flow and metabolism in the brain to tell us which parts of the brain are active. And when blood is carrying oxygen, it spins differently in a magnet than when it releases it. And we use that to tell us what's going on. Now, one of the problems has been those are huge magnets, and we've not been able to do this in a portable way. But we've had breakthroughs very, very recently in actually making our magnets smaller. This is a magnet that can actually be brought out to the battlefield so that we can actually decipher what's going on in the brain. Now, there is another technology coming down the line. Tell me if you remember this. This will not be your only Star Wars reference. So raise your hands if you know this technology. What does it represent? It's holography. Holography is the ability to actually take light that has been scattered and to reconstruct it into something meaningful. Well, Mary Lou Jepson is actually building a portable MRI by using something that the brain is transparent to, which is infrared light, looking at the scattering properties of that light within the brain and using holography to reconstruct it. So we can actually map which nerve cells are speaking in both space and time. Another major advance that's coming down the line with brain mapping is understanding the brain connectome. All those lines that you see up there, those aren't nerve cells. Those are actually the connections between those nerve cells. And one of the reasons that this is coming up is for this. Now, I don't know if any of you recognize the photograph of the man on the left. That is Francis Crick, and it's appropriate to talk about him in a section that's been devoted to genetics. He is one of the co-discoverers of the structure of DNA. So he won the Nobel Prize with this, along with Watson. And he turned to neuroscience later in his life. And what he asked was this: if we could understand, if we could map the brain, every nerve cell, every connection, every firing pattern, would we actually have reconstructed that thing that we think is the soul? Now, he posed this question almost 20 years ago. I do this every day in the operating room. So what you see here is I have an electroencephalogram on the forehead of a patient. And what I do with my patients is I take them through surgery. I watch them going from being awake and aware to losing an awareness of the outside world. In fact, anesthesiologists bring you close to being comatose, and then we bring you back. And I actually map brains as they do this. And there's a group of us throughout the world that have taken upon ourselves to actually understand the neural basis of human consciousness by examining brains that we make reversibly unconscious. Now, whoops, sorry about that. That was a little loud. One thing that has really changed what we're doing is the ability to understand neural decoders, okay? So I'm going to show you an example of 2 ways we can read minds using 2 different neural decoders. So this first one is for sound, okay? So here we go.
Have you ever been someplace noisy with a friend, maybe a bar or a concert, and they said something to you that you didn't understand? Maybe it sounded something like this. It was pretty hard to understand, right? But what if we heard a clean version of that sound?
If this doesn't work, it'll be really embarrassing.
You can understand it easily. So what would happen if we replayed the garbled version again? I'll bet you could understand it this time. The words just popped out at you. So why is this? We conducted the same experiment in order to answer this question. The first time that we played the garbled sentence, we didn't see very much activity in parts of the subject's brain that are associated with sound and understanding speech. The second time that they heard the garbled sentence, after they had heard the clean sentence, we saw a very different pattern emerge. What we found was that the brain actually changes the way that it focuses on different parts of the sound.
And by the way, that animation you saw, those were electrodes placed directly on human brains. Those are patients who are undergoing seizure surgery. And that's how they were able to come up with these kinds of neural decoders. And why is that important? There are people in the world who can't speak. Maybe they have ALS, and their vocal cords aren't working anymore. For those of you who remember Stephen Hawking, what if we had brain-machine interfaces that could interpret their thoughts, their desire to speak, and actually translate them? So that was an example of that. Well, at a lab in Berkeley, they're working on visual decoders, and you can see a reconstruction of people, what they're seeing from the back of their brain using a machine learning algorithm. And when you record from the back, you get really good edge detectors. There's a lot of color and texture information. Now, a few years later, Jack Gallant's group at Berkeley decided to redo this, but actually in different visual areas in the brain. So what you see here is actually a part of the brain that decodes meaning. So they still presented movies to this group of subjects and actually decoded what kind of meaning they were actually taking from this. Now, that's all well and good, but the real holy grail is to be able to look at the structure and the function of the brain together. And so what you see here is a reconstruction called the glass brain. And underneath, there is a structural image of the brain using magnetic resonance imaging. And superimposed on top of this is the electrical activity of the brain. So you are getting both the structure of the brain and the way it's firing the neural code at the same time. However, these were recorded at 2 different moments. And a new advance that has recently come out is the ability to actually combine structural and electrical imaging. So this is the combined magnetoencephalograph and MRI. And this is quite new and quite different. Now, let's go back to mind reading. You can actually decode what people are seeing through their eyes by imaging non-invasively the back of their head. So what other process do we actually see things? Turns out, dreaming. Can we create a dream decoder? And the answer is yes. There's a group in Japan, in Kyoto, who decided to do a similar experiment where they put their subjects in a magnet and allowed them to fall asleep. And just as they had begun dreaming, they would wake them up, bring them out of the magnet, and then they would say to them, could you describe, almost like a dream journal, what you were dreaming about? And you would see them talking about things like houses, trees, hills, statues, and they would write these things down, and they would look at the electrical activity in the brain, and they would make a connection, a data dictionary, between the subjects they were dreaming about and what their brain was saying, and they were able to decode their dreams. Now, that should give you a little bit of pause. As Bob Dylan said, if my thought dreams could be seen, they'd probably put my head in a guillotine. How many of you actually want me spying on your dreams? I don't know what you dream about, but I wouldn't want anyone spying on my dreams. So, this is something to hold on to keep in mind. In fact, this year at TED, Poppy Crum, who is the lead scientist at Dolby Labs, unfolded a new technology whereby you can actually, using an infrared camera, and by the way, you can grab these off Amazon or eBay for about $200-300. You could actually image entirely people's emotions, moods, and reactions to things, right? So how many of you have an Alexa? Oh, there's a lot. Okay. If I put, in addition to that microphone, if I embed a few infrared cameras, what if I start presenting data to you and then I start imaging and watching your reactions to what it is I am presenting to you? I've got free marketing research in your home, whether or not you like it. Again, something to think about as we start to let the Internet of Things into our homes. Now, people are trying to use mind-reading principles in order to even set new legal precedents. So lawyers are trying to admit fMRI data as a lie detector. So if you take a group of subjects and you ask them questions, and then you tell them, okay, I want you to deliberately tell the truth and then deliberately lie, what we can do is we can look at the magnetic activity in their brain, we can average it, and we can actually find patterns that tell us truth-telling, lie-telling. But there's a problem with this. It's a big data problem. There are sociopaths out there, and their brains are not wired like everyone else's. They can lie to you with a straight face. I'm sure your kids can lie to you with a straight face, and we don't actually know what that looks like under MRI either. There's a bigger problem, though, and that's this. So I'm going to set this experiment up for you. Imagine I'm a rodent, and I'm in a cage, and part of my cage is electrified a little bit. So I'm wandering around the cage, and I'm creating a mental map of the cage, and I get to the part that's electrified, and my paw touches it, and I get a little shock. So I know to avoid this part of the cage. And two things have happened in my brain. I have developed what's known as a fear avoidance response. Okay, that's a learned memory. And I've also got a spatial map in a part of my brain called the hippocampus. Well, we can actually record those signals. And guess what? That information was taken from the brain of one rodent and injected into another one. And those animals in cages that had no electricity in them had a mental map of the cage. They acted like this part of the cage was electrified, and they avoided it. So what did I just tell you? This is incredible. This was one of those moments where you go, oh my God, we just took a memory from one living organic brain and moved it into another. This isn't science fiction any longer, right? For those of you who have seen The Matrix, you know when Neo sits in the chair and something gets jacked up into the back of his head and he acquires all these new motor patterns? That's what this is. And look where else we're going. Just last year, researchers at the University of Birmingham in Alabama were able to have their subjects wear an EEG cap, record their brain signals as they were typing in passwords, and decode their passwords. In this study, they actually found that they could, by presenting pictures to people and using a recording cap, use the electrical activity in their brain to 100% identify people. So they call that a brain print. But there's a big problem with that. If you take people and you compare them to known databases in which we've actually mapped the brains of people who have alcoholism, things like schizophrenia and other mental disorders, you can actually using machine learning and using those old databases as training sets, you can actually decode in the new set of brains who might be, for instance, an alcoholic. And just imagine if you had consented to that, what kind of access that would give people into your thoughts and who you were. And so, as far as mind reading goes, I want to end this section by reminding you about the issues that surround it, especially data and privacy issues. Now, this brings me to the section of the talk where we go the opposite way, what I call writing the brain. And one of the oldest ways we have for writing to the brain is by sticking electrodes into brains. This is an example of a cartoon of deep brain stimulation for a motor disorder. And you see an electrode being inserted deep into the brain of this subject, and then a wire that comes along the outside, and it's implanted underneath the collarbone, okay? Now that has a battery, and you can turn it on and off. The surgery's done awake, right? So we have our patients, and we put them in the operating room. We actually put local numbing medicine on the outside. We take a Dremel tool, we drill a hole in their skull, remove the skull. There's some exposed brain. Well, it turns out the brain doesn't have any nerve endings in it, so it doesn't hurt once you do that. And so we put this whole assembly on top that drives an electrode into the brain. Why do we do this awake? Because we can test people to make sure the thing we're treating goes away as we're putting the electrode in the operating room. So I'm going to show you a great video. This is from the Mayo Clinic, and it's an example of a concert violinist who wanted to play the violin again. And what they did, the bioengineers at Mayo, is they put a 3-axis accelerometer on the bow, and they allowed this patient to play the violin in the operating room while they drove in the electrode to see the tremor go away. So watch this.
Brain stimulation, or DBS, was their best chance at stopping the tremor. It involved placing electrodes into Roger's brain. But there was a challenge to overcome that created a first-ever situation in an operating room. You see, because Roger's tremor was so small, it would be difficult for Dr. Lee and his team to tell if the electrodes they were implanting were in the best possible place to stop the tremor.
I started playing right away the day I came home from Mayo. I was back playing with my colleagues with Piezo 3 weeks later. Without the stimulator on, the tremor is quite pronounced.
You can see the difference. With the click of a controller, Roger can turn the electrodes on and off.
That's as smooth of a bow as I can play right now.
But when it's on, Roger's mastery of the violin is absolutely clear.
I hope that was kind of amazing for you, right? By injecting some electricity in the brain, we've restored his ability to play the violin. I want you to hold on to this because how many of you would love to be amazing musicians or elite athletes? And where would you go? Where is that line for you about how you would allow me to modify your brain? Here's another example. This is a gentleman from Brazil who is very young, and he has severe Parkinson's at a very young age. He has a DBS electrode too, and he's going to turn it off and then on again.
Temos uma amnésia, liga e desliga o DBS. Escreve que é um movimento para transmitir rápido nosso. Dois segundos.
So it's off, and he can't stop shaking. He's going to turn it on again. The tremor's gone. Okay, I am hoping, yes. I am hoping you're with me when I tell you we can write the brain again, that I can deliver energy into the brain and cure a disease. But how many of you want your skulls cracked open? How many of you want awake brain surgery? Not too many of you are going to say yes. So the key is, can we get energy into the brain to modulate it, to rewrite it without cracking open the skull? So I'm here to tell you, yes, we're finding new ways. One of the amazing ways we're finding to do this is by using sound waves, the same thing that's used to image a fetus in a pregnant woman or the heart. If you just tune it differently, you can actually get sound or pressure energy deep into the brain. We're also finding ways to deliver electricity to the outside of the brain or apply magnetic fields. Magnetic fields induce electrical currents in the brain, and we can rewrite the brain using magnetic fields. And here's something that was also just published this year. A group at the MIT Media Lab actually demonstrated that you can deploy tiny particles through the brain that are controlled by radio waves. So I'm also now telling you that we can radio control your brain. Now, one of the main people ask me all the time, is there anything for Alzheimer's disease? Just so you know, there are new blood tests coming out, which we never had before, which can detect Alzheimer's at an early stage. But the question is, what do you do with that data? So there are two recent advances in non-invasive neuromodulation. So one of them originally comes out of Canada. So Incytec is a focused ultrasound company. And they were able to demonstrate that they could disrupt something called the blood-brain barrier by introducing sound waves into the brain. Those are the blood vessels that actually go through your brain, and there is a barrier between them and the brain because the brain is a privileged place. We like to protect the brain from all the stuff circulating around the body. But it also prevents that part of the brain from draining the beta amyloid plaques that give you Alzheimer's. They got permission this summer from our regulatory body in the US to actually do tests on patients. And the very first patient in this Alzheimer's study was actually tested just a few weeks ago, all right? So this is new, completely new. Here's another one. There's a group at MIT that found if you stick fiber optics into the brain of mice that have Alzheimer's disease plaques, you could actually dissolve the plaques and improve their ability to learn and remember things. But again, do you realize that if you turn to the person next to you, all of you turn to the person next to you, okay, if you live past the age of 85, one of you is going to develop Alzheimer's disease. Right? We have a problem, right? We want longevity, right? But nobody wants longevity with a brain that's demented. So the question is, what are we going to do with all of us? Well, what this group found is that without brain surgery, they could inject light into the eyes or sound into the ears at the same frequency as the fibers that they were implanting in the brain and dissolve those plaques. So they're also in clinical trials now to see if they can use this to treat Alzheimer's disease. And they have set up a company to do this, Cognito. Other kinds of non-invasive neuromodulation. So the magnetic fields, did you realize that you can apply magnetic fields to the outside of the brain and use it now to treat depression? And this is the kind of depression that's resistant to medication. These are for people who are suicidal, and you can actually reverse that suicidal desire in them by applying magnetic fields to the right places on the outside of their brain. And I showed you those amazing examples of actually injecting electricity through electrodes implanted in the brain to treat Parkinson's. Well, groups are now working on doing that non-invasively decreasing the tremor in Parkinson's patients. And the field is endless. For instance, this is an example of using non-invasive neuromodulation to treat headaches. How many of you are migraine sufferers? I am one of them. So this is really, really hopeful for me. And again, for those of you that are interested in investment or following spaces like this, there are a lot of companies that are actually working on non-invasive neuromodulation, or what we call electroceuticals, as the entirely new frontier in treatment of brain diseases. But the real interesting one is this. How many of you are wondering if I can rewire you and make you smarter? Right? I mean, come on, imagine that, right? I'm here to tell you that you can actually apply energy to the outside of the skull and improve learning and memory. So some of the very first papers are being published in this field. And one of the questions was, if I zap the brain on the outside and I improve your memory, will it last? This study actually found that by zapping a certain part of the brain, that they could improve the subject's ability to do math problems, and the effect lasted more than 6 months. So that's really incredibly promising. Here's another one that actually, from the outside, targeted deep structures in the brain to improve associative memory. And do you realize that people are even using this to do things like improve sports performance? And not that I'm making an endorsement for it, but there's a whole new line of direct-to-consumer devices. This is a device where it actually stimulates the motor cortex of an athlete for 20 minutes, and then they take it off, and their performance and acquisition of motor skills during sports improves. This particular device is on the market to try and actually improve people's ability to learn. So what I'm saying, and again, these are not an endorsement for these companies, the science is still just slowly building. But I guess what I'm saying to you is that there's an entirely new world out there, but we're already getting to that point of augmentation. I'm going to say there's no going back, right? Let's say that you or someone next to you augments their brain by 20%, or maybe your child's brain. Does that give them a competitive advantage in terms of the school they go to? Does that then increase their earning potential for the rest of their life? And we've been talking about democratization. We need to be careful that these technologies are not only available for the extremely wealthy. So that brings me to another thing we need to be able to do. I told you we needed to understand the neural code to rewrite brains. So what are the new technologies for sensing brains? So one of the innovations has been in material science, new materials that instead of just putting them on the outside of the brain, you can actually seed the brain with things like graphene, and it stays there, and it doesn't alter the firing property of the neurons underneath them. Here's another innovation in sensors. Turns out you can put sensors now on the surface of the brain that do things like, this is for traumatic brain injury. They can sense temperature and pressure in the brain, and then when you're done measuring, they dissolve. You don't have to go in with brain surgery to take them out or retrieve them. Here's another really interesting example. That device is about the size right now of a grain of rice, and they're trying to decrease it to the size of a grain of sand. It's called neural dust. It's a wireless electrical stimulator. Here you see an example of the device sitting on a living nerve, and it's actually wrapped around the nerve with a cuff. And what the device actually is something called a piezoelectric device. What a piezo device does is it takes energy from one form and it turns it into another. So you can convert sound into electricity, or electricity back into sound. And that tiny little piezo crystal acts like an antenna. And even though it's sitting inside the nervous system, it can actually take sound waves, ultrasound from the outside, and actually modify the electrical signals inside. So that brings me to this topic. Can we use what I've been telling you, reading and writing brains, to connect our brains to machines? So does anybody know the oldest example of a brain-machine or brain-computer interface? Go ahead and call it out if you do. Say it again? No. The answer is actually a cochlear implant for deaf people. Those are the things we put into the ear of very young children when we diagnose them as being deaf at birth. So this is a surgeon I work with at Stanford, and this is a video of what happens when a child who's deaf has his cochlear implant turned on for the first time.
Here we go, it's coming back on, and he's back on again. See how he turned?
Hi, Jonathan. Stop for a second.
Yeah.
Hi. Good. Could you hear that? Hi, sweetie. Could you hear that?
So he's just heard his mother's voice for the first time. This video tells you something else, though. It draws on the fact that our brains are plastic. It's really easy to change them with experience. And this child's entire brain development will be different for the rest of his life because his hearing was restored early. So this is a sensory brain-machine interface, and we're trying to do it with all the senses, okay? So this is an example of electrode arrays that we can implant for people who are blind, and there are new advances coming out here, wireless, bionic. I want to show you another very interesting example of how you can create a brain-computer interface for people who have sensory deprivation. So this gentleman in the picture, the gentleman with the curly hair at the bottom right, is Paul Bakirita. He actually studied, he went to medical school in Mexico. He went back to the United States, and he decided he wanted to solve a problem for people who couldn't see. And so he developed this technology at the University of Wisconsin, which eventually got turned into a company. And what you see in the image above is a blind person who's wearing a pair of glasses. And those glasses have a camera on the front. And what that camera does is it images the world in grayscale. And it takes those pixels, like you see for that coffee cup, and it translates them into electrical current. You see that little white device coming off the glasses? That's like a lollipop you wear on your tongue. And what happens is every one of those pixels is translated into electrical current. White is strong, and black means the absence. And you wear it on your tongue. And Bakirita actually believed that instead of tasting this and having this go to that part of your cortex, the information from your tongue began to go back into your visual cortex. And with his device, you can see the world with your tongue. Take a look at this video.
Your brain is what really sees, not your eyes. If your eyes don't work, and you can create another portal into the brain, then your brain is what is going to interpret the world around you. Brainport is essentially a camera that translates a video image to a plate that we're wearing on the mouth.
Dad.
He tasted the word, right?
Hundreds of pixels on the plate tingle, and together they form patterns and shapes that my brain interprets as the space around me. I can see it, I just can't grab it.
So now he's climbing a rock wall with his tongue. So, yes. That's how plastic your brain is. Another point I want you to take home. Now look what BrainGate is doing for people who are paralyzed from the neck down, for quadriplegics. They're actually taking arrays of electrodes, similar to the very first slide I showed you, putting them on a part of the brain called the motor cortex. Now that part of the brain is actually what sends signals down my spinal cord to allow me to move, okay? People who are quadriplegic, they can still think, and they can still plan and want to move. And so what this device does is it actually interprets their thoughts. Look how small it is. It's the size of a baby aspirin, all right? You implant this in the head of someone, that's the motor cortex, and now when they think about moving, that thing decodes their thoughts and sends it to the outside world. This man is opening his email and typing using his thoughts alone. And the next video clip, this woman is using her thoughts to drive a robotic arm from outside herself to bring a carafe of coffee to her mouth, okay? Thoughts alone. She can't touch anything. She's not asking anyone to do it. She's driving a robot. Now imagine this. What if somebody has had a spinal cord injury, say in a car accident, or just developed MS or something like this, a stroke? Could you rescue their spinal cord so instead of having to send their thoughts to a robotic arm, we could save the cord? And this research out of Switzerland shows that this might be possible. This is a very similar electrode array. And instead of implanting it into the motor cortex and sending the information outside, what you're going to see is the thoughts of this monkey who is paralyzed are decoded using machine learning and sent to a spinal cord stimulator. Now, in this video, this monkey's dragging its leg. But when the stimulator's turned on, the monkey's walking normally. So this monkey is actually using its thoughts to restore its spinal cord. Now again, I just showed you some very invasive things, right? We're putting arrays in people's heads, brain surgery. What if I could tell you we could get a brain-machine interface into the brain without brain surgery? And that's what's happening. So this group in Melbourne, Australia, has just developed a device that's very similar to what we do if you've had a heart attack or you have a brain aneurysm that just burst, and we bring you into our catheter lab. So we put you on a table, and we shoot some x-rays to follow the device, but we don't anesthetize you. We put a little numbing medicine in your groin. We make a tiny little cut, and that's the most uncomfortable part. After that, we thread a device that we can follow with x-rays, and we thread it into your heart, or we thread it into your brain. And you're awake, and you leave right afterwards. Well, what they decided to do is coat those devices with a bunch of little metal electrodes. And now what they can do is deploy it through the groin without brain surgery. And there is a vein that sits right over your motor strip, right over your motor cortex. And so you can actually send a brain-machine interface through a vein into someone's brain. So watch this.
Hi, everyone. This is President Barack Obama. The U.S. and Australia are funding research into a device that could someday allow people to control their prosthetics with their minds and without invasive brain surgery. When implanted into a blood vessel, this network of tiny electrodes can record your brain signals, technology that has the potential to transform the lives of our wounded warriors and others with disabilities.
So that's kind of amazing too. So that might be our future. Now, for those of you who are very entrepreneurial, I mean, the big guns are all over this, right? So you have Elon Musk, who founded Neuralink. And he doesn't want the AIs and the robots to beat us, right? So he's trying to fuse brains with invasive brain-machine interfaces to make humans more capable. This guy, Brian Johnson, set up Kernel even before Elon did. And I just talked to him at the last Stanford Wearables conference, and this is what he said. Why would we not be as ambitious about our own potential as we are about AI? We're sitting here constantly talking about the advent of artificial intelligence. Well, what about humans? What about our human potential? And so he'd also like to create cognitive interfaces to improve human cognition. Again, invasive. Well, Miguel Nicolelis' group is trying to do this in a non-invasive way. That person who's paralyzed from the waist down is wearing a cap that has electrodes, an EEG cap. But when he wants to move, that thing decodes his thoughts, and instead of sending it to something outside him or to something invasive, it's actually talking to these exoskeleton legs, these bionic legs. And these legs carry him based on his thoughts. And he trains also in virtual reality. And when he imagines himself moving, he can actually see an avatar with legs like his own moving and walking him through space. And you can see an example of a paraplegic making the opening kick at the FIFA World Cup in 2014 using an EEG cap, using his thoughts to direct a robotic exoskeleton. But what's really, really interesting about these patients is that if you keep training them like this for a year, and here's the amazing thing. This looks like a boring slide. I promise you it's not. Nicolelis tested 9 of his patients after a year. All 9 of his patients who had trained this way regained some neurological function. They didn't have surgery, no stem cells, no CRISPR, no nothing. All they did was imagine that they were walking again, and they restored connections between their spinal cords and muscles that everyone thought were dead. So tell me what that tells you about your own human potential. You could take paralyzed people and restore them. What could you achieve using your thoughts alone? Now, non-invasive devices are really taking off. Here is something that was just demonstrated at the last IndieBio demo day. It's a group that's trying to take someone with ALS, like a Stephen Hawking, who can't speak. and actually use his brain waves in the form of an EEG to connect to the internet.
So go to Alexa, the first one, to let's play the music, to get the music, number 1.
Alexa, play some top 40.
Top 40 from Spotify.
Wow. Amazing. Amazing.
That's a non-invasive brain-machine interface connecting a human mind to the internet. And Mark Zuckerberg's all over that one, right? So that woman down there was actually one of my patients at Stanford. He actually wants to create non-invasive brain-machine interfaces for you to interact with all of your social media devices. So instead of typing on your phone with your big meaty thumbs, you could actually just talk to your devices with your mind. And that's not the only application. There are a lot of applications. Here's an example of a company that wants you to use your mind to interact with the virtual world, to actually navigate virtual scapes using your thoughts alone, rather than having to use controllers. And that's what brings me to the topic of robots and bionic brains. This guy that you see here, Hugh Hare, is a professor at MIT now, but when he was young, he was a mountain climber, and he lost both of his legs in a climbing accident. I hope you notice he doesn't have normal human legs, right? He's sporting bionic legs. This is him on the TED stage this year. He has an entire company where he creates custom bionics for people who have lost limbs to do all sorts of things. People who want to walk, people who want to dance, people who want to climb mountains again. He actually believes that the future is not just people who have lost limbs, but all of us are going to want to augment ourselves through something he calls neuro-embodied design. And what if you could control those with your mind? And that's what you're going to see in this video.
Human arm. It's capable of detailed tasks like using zippers, brushing teeth, and even handling fragile foods like grapes and eggs. The company has nicknamed it Luke after the character from Star Wars. Notice the similarities?
So that's the second Star Wars reference for those of you who are counting. But that's actually an arm that's controlled by the human mind. And if you don't have the $25,000 that bionic arm costs right now, you can actually image someone's stump with your phone in 3D, and you can send it to a company called Open Biotics and actually have them custom print a new bionic limb for you. And that's the approach that a lot of countries are taking around the world, including there's a place in Sudan, they've got something called Project Daniel. It's for people, especially children, whose legs are being blown off by landmines. This is a way that you can actually restore function to them. But the holy grail is, again, okay, we're controlling things with our mind. Do we get feedback coming back into our brain? I mean, I'm not walking in a vacuum. I'm getting feedback from this floor. So this scientist is actually trying to do that.
This hand exoskeleton not only induces the same range of motions as the natural hand, but also induces brain patterns of activity that are similar to when a healthy person operates the hand.
Right, so he's created artificial tendons and limbs, and somebody can move them and get the feedback sent into their brain, and it stimulates their sensory cortex to tell them where their hand is in space. So I would submit to you, we are already in the era where we are turning bionic. This is the first paraplegic cyborg games that were held in Switzerland. Again, ethics, I don't want to pretend that everything is absolutely wonderful. What are the possible uses for this? Well, we can use bionics to support soldiers, and supporting them is one thing, but what happens when we start to create super soldiers, right? What's going to happen then? And so that's something to think about. But we are definitely in the era now of the augmented human. And I want you guys now to move into a space where we're not treating diseased people, but we're augmenting all of you, okay? So here's an example, Neil Harbison. He has a form of color blindness, but he can move through the world just fine, but that wasn't enough. So he had a surgeon implant a multispectral camera into his skull, and that camera images the world in color and translates it into vibration. So he hears colors in the world vibrating. And he set up an entire movement of cyborgs. Okay, so this is his friend. Moon basically has a series of vibrational sensors in her feet. She senses earthquakes, okay, so she's a seismic sensor. There are people in this movement who've actually implanted magnets in themselves so they know where true north is, like a migrating bird. Think about this. What happens to your brain if you start adding new sense organs? Are you human anymore? I can tell you that Homo sapiens was not born with a magnetic sense like a migrating bird. Here's another example of augmentation. This is called skin put, and what you see here is someone using their forearm and hand as an entire hierarchical menu to interact with their devices. You see somebody dialing on their phone using their hand. And watch this. He is actually interacting with a hierarchical menu by tapping his forearm. And what's happening is there are vertical waves that are being sensed by this wearable around his bicep that enable him to interact with all sorts of devices. So that's skin put. This guy basically implants all kinds of devices into himself. This is an RFID that allows him to do things like turn lights on and off and heaters, just using his body but without touching anything. This guy used biomimicry. He wanted to run faster. So he built himself a set of bionic boots that mimicked the fastest bipedal running animal, which is an ostrich. And so he slaps these boots on in San Francisco on the Embarcadero, and he runs around at about 50 kilometers an hour. Right? It's kind of amazing, right? And so I submit to you, we are already in the era of the augmented human. We're already making ourselves cyborgs, right? So, are we done? No, we're not. You can actually edit the brain. We just came out of a genetics section, so I'm not going to spend too much time telling you about CRISPR, except that we are using CRISPR in the nervous system. We're using CRISPR to begin to attack diseases like genetic blindness, genetic hearing loss, genetic motor diseases like Huntington's disease. And there are entire companies now, for those of you that are interested in this space, high risk, very high risk right now, but at some point will be very, very high payoff. And again, the ethical implications that come up are we going to start to edit our germlines and create designer babies? And as Raymond has cautioned us, there's probably somewhere in the world where they have already started doing this. And then I bring you to something very creepy. How many of you want to live forever or want to be cryopreserved? Ooh, there's somebody in front. There's at least a few people. Okay, would you want to do it if I rethawed you in about 100 years and your brain was kind of mush because of the ice crystals? You know what happens when you take ice cream out of the freezer and then you put it back in? Would you want to come back that way? Possibly not, right? You want to be intact up here. Well, there are a lot of companies working on regeneration. In fact, I don't know if you know this, there are several companies that are selling cryopreservation like life insurance. Here's the co-founder of one of those companies. She's hugging a vat that has her cryopreserved husband in it, and she says, "Gee, I hope this works." So I want you to look at this graph. This is the number of people who have already put down payments to be cryopreserved. You can see that the movement started taking off in the late 80s. There are 3 companies now that dominate cryopreservation. But that question about bringing the brain back and rethawing it is a thorn in your side. So I'm here to tell you that there are companies working in this space too. Nectome just went through Y Combinator, and the head of that incubator, Sam Altman, has put a down payment to have his brain frozen and rethawed by this company. And that brings me to the subject now of connecting brains. I hope we're getting really weird and metaphysical for all of you. So anybody wonder about telepathy? Anybody kind of curious if I can connect 2 brains up? Oh, it's the front row. Okay, I am here to tell you, there have been 2 telepathy experiments done already. both non-invasive. So this one, done in 2014, this is an EEG cap that was used to read the sender's thoughts. That person took their thoughts, sent them down a wire on the internet. Someone on the other side had a magnet, transcranial magnetic stimulation, to the back of their head, and the thoughts that were being sent in bits from one sender were interpreted by the other person because they would see flashes of light. And just last month, actually about a month and a half ago, this just happened. The first social network of 3 brains was connected up using non-invasive reading and neurostimulation. And they played Tetris together. They actually played a video game together. And so I bring you back. I bring you back to all these weird things we're doing. Can we finally, do we know enough now to build a brain from the bottom up and simulate a brain? There is one group that is entirely devoted their research careers to doing that. Okay, that's the Blue Brain Project over in Switzerland. They're trying to build a brain from the ground up. They had a huge infusion of cash a few years ago from the Allen Brain Institute, and they are creating now basically neural tissue in a dish that's entirely synthetic, that is actually firing like real brains do. And then if that's true, can you do this? Can you move consciousness around? Well, remember what I told you about Francis Crick? He thought if you could build a brain and map the connectome, every connection between those neurons, you would have something that seemed like it had a soul. So we haven't managed that in humans. It's really, really computationally difficult. But what we have done it with is a worm. Worm only has 302 neurons. You can put the worm's nerve cells into software. Now you can take the firing patterns of that worm and put them into a Lego robot, and you can send an input into the robot, and the robot responds like it's a worm. So have we moved the first form of animal consciousness into an artificial construct? It's something to think about. So I close with telling you this. We are absolutely wired for transformation. And in this process, too, there are incredible market opportunities for all of you out there who are looking for them. We haven't even gone through some of them. Some people have mentioned things like addiction and motivation, but all the way from marketing decision-making all the way to human enhancement. And you should also ask yourselves, will building a sufficiently complex machine allow that machine to express consciousness? And are we soon going to be living with androids like the ones from Westworld and from Ex Machina, who all express emotions and process information? What's going to happen now that we are connecting brains to the internet? And are we ever going to get to the point where we can take isolated brains and those brains actually preserve intact our memories and consciousness? Or, as Elon Musk likes to think, are we actually just living in a programmed simulation? Are we already that sophisticated? With that, I will leave you and thank you for your attention.